Hello and welcome back to another Chemistry 141 video. Today we're going to be talking about nucleosynthesis. So nucleosynthesis is essentially how atoms can come together and fuse, and also how they can divide to form different elements. So the origin of nucleosynthesis is actually stellar nucleosynthesis, which by the name you can figure out that it happens inside of stars. So it happens inside the core of stars. So in a star, fusion is occurring, which is the combining of multiple different nuclei, okay, to form different elements. Okay, so inside of an atom, we all know that there are protons that have positive charge, there are neutrons that have neutral charge, and then orbiting around those protons are electrons. Okay, so you have electrons right here. So those subatomic particles can fuse together to generate different elements. So in stellar nucleosynthesis, we actually we start with hydrogen nuclei, okay? And then those fuse to get helium, which is currently what our sun is doing. And then once all of that hydrogen has turned into helium, the sun actually turns into what's called a red giant, and it starts fusing the helium together to get carbon, and then the carbon to get oxygen, the oxygen to get neon, and the neon to get silicon, and finally the silicon will get fused together to form iron. And at this point, the star cannot fuse any further past iron, so it will actually stop at this point. And once it reaches that point, the star will actually turn into a white dwarf. White dwarf. Or it will, if it's a larger star, it will go into a supernova and it will explode. And during that explosion, sometimes we can form the denser elements of the periodic table, which is where we get all of the denser elements that exist, is from supernovas. Okay. Also, another thing I want to talk about is fusion and fission. So fusion, as you can tell by the name, is the combining of nuclei. An example of that is, let's say you have two hydrogen nuclei. Let's just say mass number is 2. And so when you indicate, this is just how you indicate the mass number and the atomic number. This is the atomic number. This is the mass number. So this is the atomic number. This is the mass number. The atomic number is just the number of protons, and it indicates it indicates what the element is. So for one proton, that's always hydrogen. And the mass number indicates the sum of the number of protons and the number of neutrons. Protons or neutrons are also classified under the name nucleons. So both protons and neutrons are nucleons. Okay, so if you take if you fuse two hydrogen nuclei together, what are you going to get? Well, you're going to get a helium nuclei, which looks like this. Oops, that should be 4. Okay, so that's an example of fusion. And then fission, on the other hand, would be the reverse. So you take one nuclei and you split it into 2. So, and the example of that would be taking to take one large nuclei and split it into multiple nuclei. That would be the reverse. So you would take a helium nuclei and you would split it into the 2 separate hydrogen nuclei. That would be an example of that. So that's fusion. That's fission. So fission are like the atomic bombs that we use. Although now we have the thermonuclear bombs. Those are fusion bombs. So like a hydrogen bomb is actually doing this kind of fusion. Fusion tends to release more energy than fission does. But the first The first atomic bomb that we ever used was a uranium bomb. We also had plutonium bombs. Those were both fission bombs, and they released less energy. Nuclear power plants also use fission. They have not figured out how to generate energy via nuclear power plant via fusion yet, but it is being worked on currently. Another thing I wanted to mention is we have certain kinds of radioactive decay also. Okay, and there are 3 types of radioactive decay that you should know. So there's alpha decay, there's beta decay, and gamma decay. All right, and then with alpha decay, that is the emission. So all radioactive decay emits a particle, and it changes the nucleus that did emit that particle. So for example, let's say we have carbon, and carbon has a mass number of 12 and an atomic number of 6 most of the time. Let's just say this carbon emits an alpha particle. What would that look like? So what would happen is an alpha particle would form, and an alpha particle looks like this. So it's a helium nuclei. An alpha particle is always a helium nuclei. So emit a helium nuclei plus whatever's left over, because we have to make the equation equivalent. So 12 minus 4 equals 8, and 6 minus 2 equals 4. Okay. And so whatever element has 4 protons, that's what it would be. I think that's boron, if I remember correctly. And then beta particle would look a little bit different, because let's just say we start with the same carbon atom. We would instead form a beta particle, which looks like this. And again, we have to make our equation equivalent. So it's going to be 12 still, but on the right side, it's going to be 7 instead of 6, because we gain a proton in the original material. So instead of carbon, it's going to be nitrogen. All right, so that's beta decay. That's how beta decay works. And then gamma decay is a little bit different, because it doesn't emit any mass, so it doesn't emit protons or neutrons. Instead, it emits a photon, and a high energy photon. Okay. And one last thing that I want to mention is, well, actually a couple more things I want to mention. Isotopes. So an isotope is just a type of nucleus that has the same number of protons, but it has a different number of neutrons. So an example of that would be, like, let's just say we have a hydrogen atom that has, hydrogen atoms always have 1 proton, but one hydrogen atom could have 2 nucleons, 1 neutron and 1 proton, and that would be called deuterium. But if it has 3 nucleons, 1 proton and 2 neutrons, that would be tritium, another isotope of hydrogen. So you see that even though they have the same atomic number, the same number of protons, if they don't have the same number of neutrons or the same mass number, then they'll be isotopes of each other. And then the last thing that I want to mention is that when bonds are formed between subatomic particles, when bonds are formed, energy is released. And when bonds are broken, energy is absorbed. And in order to figure out the amount of energy that is either released or formed, you're going to use the equation E equals mc squared, the very famous equation. Because what actually happens when you do fusion of two particles, they actually lose a little bit of mass when they fuse together. And the theory is that that mass is converted into energy. So essentially, if you want to calculate how much energy was produced during the formation, during that formation of that bond, you would calculate how much mass was lost overall, multiply that by the speed of light squared in meters per second, and that will tell you how much energy in joules that was produced. So that's nucleosynthesis. Thank you for watching.